Chapter 17 on equilibrium. Chapter 17 is a monster chapter, and I know you're feeling overwhelmed with all that Chapter 17 appears to have, but keep in mind this is a building chapter because chapters 18 and 19 just continue with applied applications of equilibrium with acids and bases in Chapter 18 and then other kinds of solution equilibria in Chapter 19. So it's really important that we get equilibrium to be something that you're very familiar with and comfortable with. So as kind of a way to just introduce this first sample problem, I just wanted to take a second and highlight the 5 things that are important from Chapter 17. The first thing that's important is thinking about just the concept of equilibrium. And then when we think about the concepts of equilibrium, we need to think about equilibrium constants. And equilibrium constants are going to be what we call big K, so a capital letter K. And we find them in flavors of Kc and Kp. And that C and P stands for ways that we represent the amounts of materials that we have, either as concentrations in molarity, or P stands for pressures in atmosphere. So equilibrium constants are ways of looking at how much product or reactant we have. Lastly, kind of under the same category, is the idea of a reaction quotient, where we think of that as Q. And in your summary sheet, it talks about the idea that Q represents kind of the concentrations of species where you are, and K represents the concentrations of species where you want to be when you're at equilibrium. So the idea of comparing Q versus K is going to be our next concept here, is predicting reaction direction by evaluating Q and K. So predicting reaction direction by looking at Q versus K. And we'll have some sample problems that practice that. Probably the biggest part of this chapter, and where most of the sample problems and where most of the homework problems lie, are dealing with equilibrium problems. So again, there'll be lots of sample problems to kind of deal with this, but we're building up through these earlier kind of key concepts, aspects that will build into equilibrium problems. The fourth thing that's kind of important is something that we call Le Chatelier's principle. And this is a way to think about how equilibrium can shift. So we'll get to that, and then the last thing is actually practical applications. So those are the 5 things that are going to become important in this chapter. And starting right off here with our first sample problem is the idea of writing reaction quotients from balanced equations. And the idea of a balanced equation is really important here because, as we'll see, the coefficients from balanced equations become part of our reaction quotients. So we can write reaction quotients. Again, they give us 2 reactions here. So the first reaction tells us it's the decomposition of nitrogen pentaoxide, and in this case into nitrogen dioxide and molecular oxygen. So the first thing that we need to do is make sure that we have a balanced equation. So N2O5 gas decomposing to NO2 gas plus O2 gas. And again, I'm giving some room in front here so that I can write coefficients as we see whether or not we need to balance this. Just looking right out, I can see that there's 2 nitrogens on the left and only 1 on the right. So we absolutely are going to need to balance this. And I can already see, looking over here, we have an odd number of oxygen atoms on the left, and we're always going to have an even number on the right. So already I know that I'm going to want to scale up this on the left. So I'm going to start by doing that, which gives me 10 oxygen atoms on the left, and it gives me 4 on the right here. 4 nitrogen atoms, if I put a 4 in front here, that satisfies my nitrogen, but it also happens to satisfy my oxygen. So here's the balanced equation for the first reaction. And again, it's very important to balance the equations, because if you don't balance the equations, the coefficients won't be correct to become part of your reaction quotient. So to write a reaction quotient, you can either write it as Kc or Kp. Again, when we write it as Kc, this stands for amounts as concentrations, and the units will always be molarity. So we can write Kc as the concentration of NO2 to the 4th. So O2 and N2O5 squared. So reaction quotients are written as the product of the products, so product meaning multiplication, the multiplication of the concentration of products raised to powers that are coefficients in your chemical equation over the product of the concentration of reactants. There's only one reactant in this first species. So in this case, we've got N2O5 raised to a power that is a coefficient. That's how we write reaction quotients. Products over reactants, and it's the product of the products, so the multiplication of the concentration of products raised to powers that are coefficients. So this is where it's really important that you make sure you don't confuse stuff that we did in kinetics, where I told you time and time again, you cannot use the coefficients from the balanced chemical equation to become exponents in your rate law. You have to determine them experimentally. Here we do. So you've got to make sure you reconcile those early so that we don't get confused as we're working on our next exam with both equilibrium and kinetics problems. All right, let's take our next problem here. C3H8 plus O2 gas gives us CO2 gas plus H2O gas. Now, this asks us to calculate or to write reaction quotients as QC for each of these. But again, we'll see in a little bit we can have QPs, and QPs represent amounts of materials as partial pressures and atmospheres. So we'll get to that a little bit later. So let's continue with our QC. Looking at this equation, again, we have to make sure that it's balanced here. And going through, I can see I'm going to need to put a 3 to balance my carbon atoms here. Going through to balance oxygen, I can already see I'm going to have an odd number of oxygen atoms if I don't do something over here. 8 hydrogens, let's put a 4 here, see if that works. Now we've got 4 plus 6 is 10 oxygen atoms. Putting a 5 here, going back through, our equation is completely balanced doing it in this way. So QC then, again, product of the products raised to powers that are coefficients over the product of the reactants. So we've got the concentration of CO2 cubed times the concentration of H2O to the 4th over the concentration of C3H8 times the concentration of O2 to the 5th. Now keep in mind, don't worry that we've got large numbers that we have here. These are not reaction orders. This is not kinetics. This is equilibrium.